This is lesson 6.5, applications of linear transformations. A little bit of a lighter lesson compared to the past several that we've had. In this lesson, we're going to simply look at some geometric transformations, applying matrices to do those. So looking at things like reflections, rotations, what's called a shear. Let's go ahead and jump in and just take a look at these. I'm not necessarily planning to do a whole lot of examples. I think these are pretty straightforward. But I just want to kind of walk through and explain what they are and maybe why they work. So the first set deals with reflections. We have a reflection in the y-axis, in the x-axis, and in the line y equals x. Most of the work that we're going to do in this lesson is going to be in the R2 space, but we'll finish up with rotations in the 3 space. So if you think about reflection in the y-axis, basically what we're saying here is we're going to take a point in the two-dimensional plane, and we're simply going to reflect that point, kind of a mirror image, over the y-axis. So if you think about the fact that we've got a point xy, if I reflect it, the y is going to stay the same, but the x is going to be exactly the opposite. So if you look at the matrix then that we would apply to make this happen, notice that we've got a -1 in the upper left corner. We've got a 1 in the lower right corner. So that -1 is simply going to take that x and make it a negative. The 1 in the lower right is going to keep the y as just y. Okay, so, again, I mentioned I wasn't going to do a whole lot of examples here, but just as a real quick example, if I had the point 2, 3, no, not fractions, we're dealing with matrices here. So 2, 3. And I multiply, I'm going to get -2 and 3. And so again, thinking about what I just mentioned, I would have a point at 2, 3, and we're reflecting it across to -2, 3. That's a reflection in the y-axis. The other two, the x-axis and y equals x, similar idea. So x-axis, straightforward, we're just going vertically reflecting instead of horizontally. The y equals x here, if I've got the line y equals x, and I take a point, xy, when I reflect that over the line, in this case, basically the x and the y switch. The x becomes the y becomes the x. And so again, when you look at that matrix, we can see how that's going to happen, where if I even just take a just generic point xy, if I multiply, I'll get 0 times x, 1 times y is y, and then x in the bottom. So this actually creates the ordered pair yx. All right, the next set are the expansions and contractions. We're going to look at horizontal and vertical. Now, you may remember back in your geometry days doing transformations, and one of the things that you would have done is contractions and expansions, but at that time, you would have done something like this. You would have had a vector or just a point, and you would have expanded or contracted that point in relation to the origin. So maybe you had a vector or a point that you wanted to contract by a factor of 1/2, and so you'd take both points and you basically move this in half the distance, and that would be a contraction because you're dealing with both the vertical and the horizontal together. In this case, we're talking strictly about just a horizontal or just a vertical expansion or contraction. So pictorially, what that looks like is I have a vector. And if I want to contract that vertically, for example, again, let's just use the example of 1/2, I would only be concerned with the vertical. So I'd literally contract this by a factor of 1/2, and that would be my new vector. Or if I did it horizontally, same idea. Let's say I wanted to expand it by a factor of 3. Horizontally, I'm just simply going to focus only on the horizontal. So in a horizontal expansion or contraction, the vertical stays the same. In the vertical expansion or contraction, the horizontal stays the same. And again, you can see that we're in the horizontal. The one in the lower corner is going to keep the vertical the same. In the vertical, you have it in the upper corner. That's going to keep the horizontal the same. And then we just pick a k value, and that k value is going to determine then what kind of contraction or expansion it is. All right. Horizontal and vertical shear. This was actually a much lesser known one. Most people don't really know what a shear is. It's not something we talk too often about in math. It's similar to a contraction or expansion. The difference is that in this case, rather than directly expanding or contracting the x or y value, you're doing so in relation to the other value or in proportion to the other value. So whereas again, in what we just did, I might take the horizontal, and if I want to do a horizontal expansion or contraction, I am multiplying the horizontal value by a number. And that's going to stretch it out left or right, or contract it left or right. Same with vertical. If I want to do a vertical expansion or contraction, I'm multiplying the vertical number to create that expansion or contraction. Here, the way that this works, and I'm just going to do this just by example to show you. Let's take a point like 1, 2, and I'm gonna let this k value be 3, for example. So we're going to do a horizontal shear of 3. When I multiply this out, what I get is 1 and 6 is 7, and then 0 and 2 is 2. Okay, so notice that it's a horizontal shear, and it's the horizontal number that changed, right? This is the ordered pair, then 7, 2. Okay, or the vector 7, 2, I should say. So here, what's happening is we started with a point at 1, 2, and that point has now moved to 7, 2. So our vector would have looked like this. Now our vector looks like this. But we didn't multiply the x value by 7. We actually multiplied the y value by 3, and it was the y value that actually created the horizontal stretch or contraction. So it's using a proportion of y to create the horizontal. And then likewise, a vertical shear, same idea. In this case, if we just had the same point 1, 2, my vector is either going to go up or down, contracted or expanded up or down, but again, not in relation to y, but rather in proportion to x. Okay, so that's what a shear is. All right, let's get into rotations. And this is actually something that I passed over in 6.1 intentionally because I knew we were going to be coming back to some of this here, and I thought it would just fit better here. So this part right here is actually out of lesson 6.1 or section 6.1. And it's a rotation in the 2 space. So again, in 2 dimensions. So this is where I have a vector. And I want to specifically rotate that vector in a counterclockwise direction a certain number of degrees. So in this case, if I rotate, let's just say 30 degrees, and we're going to assume that this is a 30-degree angle, it would be in a counterclockwise direction over the angle 30 degrees or through the angle 30 degrees. And the way that we create that transformation is through this matrix shown, this matrix right here. So obviously if I'm doing 30 degrees, I'm just going to make all of my thetas 30 degrees. And then I would multiply by the original point. So let's just say this original point happened to be 4, 2. I'm just going to multiply this by 4, 2. I keep doing fractions. I don't know why. All right, 4, 2, there we go. And so I would just obviously take sine of 30 times 4. In this case, minus 2 sine 30. I would get that value, and that would be my x value, and then same for the second row and the column, and that would give me my y value. And that would just tell me what this point is. Okay? All right. In 3 dimensions, it depends on which axis you rotate about. So we're going to look at all 3 of those. So kind of a similar concept as 2 dimensions. Obviously, we've got another axis to think about, and so it creates a 3 by 3 instead of the 2 by 2. In this case, what happens is you've got kind of this idea of the sines and cosines in 4 of the positions, just like we do in the 2 space, and then the other positions are filled with zeros and a single 1. Okay, and it just depends obviously on what we're rotating about. So in this case, if we're rotating about the x-axis, we have the matrix shown here that we're going to multiply by for the y-axis, for the z-axis. So again, just very, very simply, just to get an idea of what this looks like. So here's my, try to draw this here. Let's say this is my x-axis, and this is my y-axis, and this is my z-axis. If I want to take an object or something, and I want to reflect it over the x-axis, Maybe I have, we'll just do a little box here. Let's see if I can draw a box here. And all right, you get the idea. There we go. All right, so I've got my little box, and we want to reflect this about the y, or rotate it, excuse me, about the x-axis. Obviously, then I'm just taking this and I'm rotating it around that x-axis. Okay. Same for the y, same for the z. Just using those matrices, just like we did before. All of this is like I said, it's very, very straightforward. You simply have a point and you're simply multiplying that by one of these matrices depending on what kind of transformation you want to perform. Not really anything more to say than that. I think it's that straightforward. I think you'll be able to do the exercises just fine. Do reach out though if you do have any questions, and I'm happy to add more detail to this. So with that, I'm going to leave it to you, and I will see you in Chapter 7 in the next lesson.